Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about inductance and inductors. So this introduces another circuit element of sorts for our introductory course. It is probably the last new circuit element as such that I would introduce in an introductory course. This element basically makes use of Faraday's law to produce what's called a back EMF. So let's unpack all of that, shall we? Let's begin by recalling what it is that Faraday's law says. Faraday's law basically says that the induced EMF for anything really, a closed circuit, if you will be given by the rate change of the flux of the magnetic field through that circuit. So we can write that as epsilon is negative in d phi sub b by dt, or we could write it out in its sort of more explicit form, n times d by dt, that is the time derivative of the integral of the magnetic field dotted with the area vector. Okay, so that's Faraday's law. Now, Faraday's law should apply to any system in which we have a magnetic field that changes, or an orientation that changes, or a closed loop that size gets larger or smaller. Anything that is changing either the magnetic field or the area or the relative direction between the two of them. So, for example, if you have a circuit and you maybe have like a voltage control where you have a power supply, you turn the voltage up or down on the circuit, that will make the current go up or down for that circuit. And by doing that, you're changing the magnetic field which is produced by that current. So if this represents my circuit and I've changed the current through the circuit, then I'm going to be changing the magnetic field flux, and that means that I should get what's called a back EMF. And the basic train of reasoning here might be, for example, if you increase the voltage, then you're expecting to have more current in the circuit. That is in turn going to produce a bigger magnetic field by Ampere's law, which is going to produce a bigger flux from the magnetic field, and so you will therefore get an EMF that is sort of opposed to this power supply. It'd be like putting in a second power supply with a reverse polarity. And the same is true if you decrease the voltage and therefore decrease the current, and therefore decrease the B field and the flux. You'd get a new EMF that sort of is in the same direction as the polarity of the original EMF. Okay, and so this is sometimes what's called back EMF. Basically, among other things, it means that when you turn a device on, it doesn't actually instantly come on. There is actually sort of a rise time until it is on. It's just that that rise time is often very, very fast, so we don't notice it. Now, all of that is a bit of a mouthful to have to say every time that we want to talk about a back EMF. So we can introduce this new idea called inductance. And inductance we often represent with either an L for self-inductance or an M for mutual inductance. What it does is it sort of gets us around having to figure out magnetic field fluxes every time, and instead focuses on this sort of term here, more current or less current, rather than bigger flux or smaller flux. So essentially what we do here is, instead of having to figure out how is the flux going to change in the situation, we figure out how is the current going to change in the situation, because the flux often depends upon the current, at least for fixed circuit devices. Now, before I get too far down that particular explanation, it's worth noting that we do care more about current than changing the voltage or the EMF, since in order to figure out how the flux will change with those, you also have to know more information about the system, such as what's the resistance, and ergo what is the current, and ergo etc. Current you can measure directly using the ammeter, and so that's why we care or prefer to work in terms of current. So the other thing is that there are two types of inductance that we could talk about: self-inductance and mutual inductance. Self-inductance basically means you have a single device or system with no really moving parts other than just that you're changing the voltage or changing the current. So in some sense, this entire illustrated example of a circuit that I'm changing the current in is a sort of self-inductance. Mutual inductance happens if you have one device being changed and it causes a change in the other. So self-inductance, basically you're expecting there to be one device or maybe one circuit involved, and if you make a change to the current in that device, then you get a back EMF in that same device. With mutual inductance, you have two or more devices, and changing the current in one of the devices causes there to be an induced EMF in the other device. Now, of these two, the definition for each is kind of similar, but how you go about calculating one or the other is somewhat different. Self-inductance is usually easier to determine than mutual inductance for a given type of device versus pair of devices, because you don't have additional factors like how are the two devices oriented relative to each other and how far apart or how close are they to each other. Okay, so that's stuff to keep in mind. So how are these two things defined? What's the equation that defines? Well, self-inductance is defined by noting that the back EMF within a device is going to be given by the self-inductance L times the rate change of the current in the device, di dt. So our self-inductance, of course, is L. Our mutual inductance is M. There's only one device here, so we only have to worry about one current and one back EMF. There is a sense, by the way, in which L, therefore, is equal to something like the number of turns times the flux of the B field divided by the current in the system. But I'm not going to worry about that at the moment. Instead, how do we do mutual inductance? Well, mutual inductance is defined in such a way that if I have two devices, the second device will have a back EMF equal to negative of the mutual inductance times the rate change of the current in the first device, and the EMF in the first device will have negative M times the rate change di by dt of the current for the second device. So both of these equations are actually true. The mutual inductance is valid for both. So once you've found the mutual inductance of device 1 acting on device 2 or with regard to device 2, you've also found the mutual inductance of device 2 with regard to device 1. So that's how these guys are defined. For mutual inductance, examples do exist, and there are some relatively simple mutual inductances that you can calculate. For example, a pair of embedded solenoids are usually relatively straightforward because we know how current and how change in current is related to the flux or change in flux of the magnetic field for one or the other of the two ideal solenoids. Ditto for toroids, etc. Self-inductance, usually you have to ask, okay, if I make a change in this current, what is that going to do to the magnetic field, and what is that magnetic field in turn going to do to the flux of the magnetic field through this device? So in some sense, both of these have to be kind of calculated for different devices, but the good news is once you've calculated it for a type of device, at least in self-inductance's case, you basically now have the answer for that device, be it a toroid, be it a solenoid, be it a coaxial cable, etc. With mutual inductance, you kind of have to go back every time there's any change, like, oh, I moved one of the two devices relative to the other. Now I have to go recalculate it. One other thing that's worth noting is that there's a circuit symbol, maybe two other things. One is the unit. So what's the unit for self or mutual inductance? They both have the same unit. It is the Henry. And the Henry is defined to be 1 Henry is equal to 1 ohm dot second. All right, so those are your units, and that's true for both of these, both the mutual and the self-inductance. All right, what else maybe do we need to say here? Well, I said a moment ago that it's a circuit element. And so for self-inductors, which are often just called inductors, there's kind of two common ways of drawing the circuit element. You can either do something like this, where you have this sort of like bouncy loop, or you can draw it to have actual loops for the circuit elements. So sometimes an inductor in a circuit is drawn like this. Either of these is valid. Mutual inductance, a little harder to convey, but a common type of sort of mutual inductor, if you will, in a circuit is a transformer. And so that is often drawn as just a pair of inductors side by side like this, often with a set of dashed lines between the two of them, or dotted lines between the two of them. Sometimes the solid lines are used instead of dashed lines. It's usually two lines between the two, and it can either be this version or this version on either side. So for what it's worth. Let's do maybe one quick example of self-inductance. For our example, let's consider a coaxial cable with length little l, and R inner and R outer, Ri and Ro. Worth recalling, the magnetic field for a long straight wire is mu naught I over 2 pi r. That's from Ampere's law, outside of the wire. And if you have a shell of a wire, your outer conductor, in other words, it's basically not producing much in the way of a field on the inside. Okay, so geometry wise, your coax cable from the end would basically look like this. And so this right here would represent R outer, this right here would represent R inner. And let's take a magnetic field produced by this wire, which is like so. Then this would be distance R for the Ampere's law equation. Alright, so I've drawn both an in view and a side view of this situation. Essentially, you have your magnetic field that's being produced by the inner conductor carrying a current. The outer conductor actually carries a return current, so the current's in the opposite direction and of equal magnitude. So you have field in this region between the two conductors. You don't have any field out here outside of them. The relevant area vector ends up basically just being the area vector that you would see essentially right here. And so if I wanted to write a dA vector, dA would be dr times L. It's basically like a long thin rectangle of height dr and width L. This lets us calculate what our d phi b term would be, and so then in turn this is basically like b times L dr. And then in turn, essentially we would just do the integral to get phi b. Now, making use of this Ampere's law to substitute for the magnetic field. We basically therefore get that phi sub b is equal to integral from the inner to the outer of mu naught times I divided by 2 pi times r times L times dr. And so upon integration, we know that most of this stuff is constant relative to dr. You basically have a bunch of constants and then a 1 over r dr. You know that 1 over r integrates to the natural log of r. And so this ends up looking like mu naught times I times L divided by 2 pi times the natural log of basically r. So we could just put an L in r. Well, that in turn means that phi sub b is equal to basically this mu naught IL over 2 pi, so mu naught IL over 2 pi times the natural log of r outer minus the natural log of r inner. And so that in turn ends up just being mu naught times I times L divided by 2 pi times the natural log of r outer over r inner. We're just making use of the well-known information that the difference between two natural logs is the natural log of the quotient of the arguments. Alright, so that gets us what phi b is. Now recall that epsilon is equal to n, or is equal to negative n, times d phi by dt, and that is also equal to negative of L times di by dt. Okay, so putting these things together, L should look like n times d phi b by dt divided by di by dt. So in some sense, you should be able to cancel these dt's if you'd like, and your L should just look like n d phi sub b by by di. And so looking at this right here, if this is phi b, if I take a derivative with respect to I, then the current is to the first power just becomes a 1. And so my L is just equal to mu naught times the length little l divided by 2 pi times the natural log of the outer divided by the inner radius. Now oftentimes if you're doing like engineering stuff, it's maybe more convenient, instead of finding the inductance of a coax cable, to find what's called the inductance per unit length of the coax cable. And basically what that lets you do is, instead of having to calculate it each time that you have a different length of coax cable, you just simply calculate it for coax cables in general, and then that's per unit length, and then you just multiply by the length of whatever you've cut to, and that gives you the self-inductance now for that coax cable. Alright, so that's a nice little example, and that's basically it for today's video. Hopefully it has helped you understand this subject a little bit more. Hopefully you learned something from it. As always, thanks for watching.